Welcome to Physics 202 Online. Today we're going to talk about magnetic fields. We've already started to talk about this in class, and I want to go over a few things and see if we can move ourselves along. Right now, this corresponds to chapter 28 in the new text, chapter 29 in the old text. First of all, we define the vector B, and it's got three names. Typically, we use the term magnetic field for B. You may also hear it referred to as magnetic induction, or sometimes magnetic flux density. All of those things are names for a magnetic field. Magnetic field will do fine for us. One of the differences that you'll see about magnetic fields and electric fields is forces only happen if you have a moving charge in the case of magnetic fields. In the case of electric fields, you can have stationary charges as well. What do we know? So far we know that magnetic force is proportional to the size of the charge of the particle. It's proportional to the speed or velocity of the particle, and it's proportional to the size of the external magnetic field that it happens to be traveling in. Remember, in this chapter we're talking about magnetic fields that are external to the system. Yes, we know that current carrying wires produce magnetic fields, but we're not worried about them right now. Okay, if we put all this together, we find, as we mentioned before, that the magnetic force on a moving charged particle is equal to QV cross B. You know the cross product is just the magnitude of V times the magnitude of B times the angle between those two vectors. Okay, so that's a very nice expression for magnetic force. When we want to determine direction, we've done this before, but I want to illustrate it again. Use your thumb to illustrate the direction that the charge is moving, if it's a positive charge. Use your extended fingers to indicate the direction of the magnetic field, and use your palm to indicate the direction of the magnetic force. So in this case, if the particle is moving from my right to my left, and the field is pointing towards you from me, the force on that particle would be down. If it happened to be a negative charge like an electron, the force would be pointing upwards. Okay? As I said, we have a difference between magnetic forces and electric forces. Magnetic forces point in a direction that's perpendicular to the direction of the magnetic field. Electric forces always point in a direction that is either parallel or anti-parallel to the field itself. Another difference, electric force does work as it displaces a particle, a charged particle. Magnetic forces do no work because the force is perpendicular to the direction of motion of charge. That cross product then would be zero. Dot product would be zero, sorry. We've said this before, but let me indicate it again. Our units for magnetic field are the Tesla. 1 Tesla is a very large magnetic field. It's equal to 10,000 Gauss. That's the old time unit that we used to use for a magnetic field. Typically, we express smaller fields in terms of Gauss. For example, the Earth has a magnetic field of about half a Gauss. Okay, so just to give you an indication, we talk about say the magnetic field for an MRI machine. That's about a Tesla. If we have conventional lab magnets, there may be 2.5 Tesla. If we have superconducting magnets like we might use in a collider or a particle accelerator, they're going to be more like on the terms of 25 Tesla. So even 1 Tesla is a very huge magnetic field. We've done cross products before. I think probably we'll just as a review set this up. Suppose I have a particle that has a velocity vector given as 5I plus 3J minus 2K, and it's subject to a magnetic field that has a vector 4I minus 2J plus 6K. If I want, let's say it's an electron, if I want to find out the force on that electron, I'm going to say that I can calculate as E, the charge of the electron, in fact minus E, times V cross B. Now when I want to find V cross B, I set up my cross product with my ijk unit vectors, and then the coefficients of the vectors, the velocity vector 5, 3, minus 2, 4, minus 2, and 6 for the magnetic field vector. When I do the cross product, when I want the I component, it's 3 times 6 minus 4, so that's going to be 18 minus 4 is 14. I, it's going, if I use this, it's going to be minus 8 and a minus 30, so it's going to be minus 8 minus 38 J. And then for the kth component, it's going to be a minus 10, minus 12, or minus 22 K. That's going to be the size of V cross B, or actually the vector V cross B. When I want to find the force on the electron, then it's going to be minus E times 14I minus 38J minus 22K. So that's the way you might calculate the force on a moving charged particle in an external magnetic field. One of the other expressions that we might use is to calculate the magnetic force on a current carrying conductor, current carrying wire. Let's have a look at this. This is kind of an interesting derivation to come out with a very simple result. So I can think of it this way. Consider a straight segment of wire of length L, and let's say cross-sectional area A. Let's say that it's carrying a current I in a uniform magnetic field. Let's say the field is going into the blackboard, some uniform magnetic field that we'll call B, okay? And so we may look at the way this works in the following way. Suppose I can say that the force on a charge moving within this wire. Remember, you may not have a power supply driving charges through the wire, but the charges themselves will be moving with a drift velocity. We'll call that V sub D. So the drift velocity across the external magnetic field that the charges are in will provide the force on that current carrying wire. And let's derive how we get this. Suppose I have a number n of charges per volume such that n times the area times the length of the wire will give me n, capital N, the total number of charges. This means that if I have a force on the wire, it's going to be equal to the force times N times A times L, the number of charges, times the charge of each charge, times the drift velocity across the magnetic field. That being the case, there's one other thing to keep in mind. We know from chapter 26 that the current can be written in terms of the number of charges per volume times the charge times the drift velocity times the area. That being the case, if I put that all in, notice what's going to happen. The force is then just going to be equal to I times L cross B. A very simple expression for magnetic force on a current carrying wire. I know that's kind of a long way around the world in showing this. And as I said before, the drift velocity is very rarely used in this course, but it's one way that it comes in is in this derivation for the magnetic force on a current carrying wire. Now this only works for a straight segment of wire only, but we can do something. If I have a curved segment, I can do the following. I can break the curve up into little pieces of current, little bit, we'll call it ds. If I want to do it that way, and let's say I'm putting this thing in an external magnetic field that looks like such, if I want to find the force on this whole wire, I can look at the force on each particular segment of current, and I can write that force is equal to the current in that segment times that length of segment across the magnetic field. In this case, if I'm drawing it this way, if B is going upwards, the magnetic force is coming out of the page. I can write the total force, and all I have to do is integrate to find the total force, and that force is going to be equal to the integral of I ds cross B. And as long as the geometry is fairly simple, this becomes a very simple idea. So for example, if I'm in a uniform magnetic field, and the field is perpendicular to the current element ds, I can pull that out of the integral, and I can write my force, again, if it's a constant current, as I times the integral of ds, this way, cross B. The integral of ds, if B is a constant, is just going to be the length of that line segment, and so I can write that as just IL cross B, where L is just the length of this line segment, and that's just the integral of ds. On the other hand, I can take an arbitrarily closed loop. So for example, I can have a loop that closes, and I can put that loop of current in an external magnetic field. And so we'll find that in this case, the force is equal to the constant current I going through this segment times the integral of ds, but it's around a closed loop cross B. But notice, if I'm integrating this in a constant magnetic field, this closed loop, there's no displacement whatsoever. So the force for any external field on a closed current loop is always going to be zero. No exceptions. That's always going to be the case. So that's a very important point that we can make from this. If I have an open loop, then the force is going to be calculated using this expression or this expression. If I have a closed loop, though, that force is always going to be zero. It's a good thing to remember.